Planet Semicon welcomes you to explore the field of semiconductor physics and technology, the foundation of microelectronics and VLSI design engineering. In VLSI design, a library serves as the foundational database that holds pre-characterized information of logic gates. These libraries are crucial for design, simulation, timing verification, power analysis, and ultimately, successful chip fabrication. Library contains models of characterized CMOS gates with characteristic parameter. Parameters are generated through simulation or silicon characterization and stored libraries. Libraries are critical to ensuring design accuracy, performance, and manufacturability. In this video, we will have an overview of parameters, characterization, models creation of a logic library gates. So let's get started. The VLSI design flow shown consists of logical and physical design and fabrication process. Using EDA tools, simulation models, and process-specific libraries, the conceptual idea is transformed into silicon chip. The VLSI design methodology can be broadly classified into three stages, namely, logic design the front end, physical design the back end, and fabrication that process the silicon chip. The logic design focuses on functionality of the chip. Transforms specifications into RTL-level functional code. The physical design transforms code into the chip physical layout design that can be fabricated in the targeted foundry. The foundry converts layout into silicon chip that realizes the desired electrical functionality. In VLSI design, a library is a repository of pre-characterized models that define the electrical, physical, and functional behavior of gates used in the design and verification process. A model is a virtual characteristic representation of a logic gate. Modeling is the process of developing a mathematical abstraction of a gate, enabling analysis of its behavior under different operating conditions. This avoids the need for physical fabrication at early stage. Characterization is the process of measuring or simulating the gate's behavior under various operating conditions. These results are stored in library formats and are used in simulation and verification purposes. In this video, we use the basic CMOS logic gate inverter to demonstrate modeling and characterization of logic gates. Various steps involved in creating a logic library are presented below. Gate modeling starts with creating N and P MOSFET SPICE models of required levels. In order to capture the impact of transistor parameters on gate behavior, include threshold voltage, mobility, channel length modulation, parasitic capacitance parameters in the model. Build functional MOS transistor level gate circuit. As per the functional requirement, build the MOS transistor level logic gate circuit. Functional verification. Apply relevant test vectors to verify logical functionality of the gate. Performance evaluation. DC characterization evaluates the static behavior, creates voltage transfer characteristic VTC curve. AC characterization evaluates dynamic behavior to assess switching performance and propagation delays. Power characterization evaluates leakage power, dynamic power, short circuit power. Using the above data, create different types of models such as SPICE models for quick estimates and approximate behavior of fixed delays, and nonlinear models NLDM table lookup models to capture realistic delays at different operating conditions of load and input slew. For each model, a standardized naming scheme, along with the symbolic visual representation, is created. Repeat the above operation for different types of functional gates and blocks. Group them into and create different functional libraries. Static parameters of a CMOS inverter describe its steady state or behavior when the input is held constant and no switching occurring. These parameters specify logic levels, noise margins, and overall logic functionality. Key static parameters for CMOS inverter are: VOH, VOL represent the high and low state output voltage levels. VIH, VIL represent the high and low state input voltage levels. NMH and NML represents high and low state noise margins. VTH, the logic gate threshold or trip voltage, indicates the gate switching or voltage transition. DC transfer characteristic represents the inverter static behavior. CMOS inverter is a basic digital logic gate built with N and PMOS transistors, connected in a complementary configuration. PMOS, the pull-up transistor, pulls the output load to high logic state and NMOS pulls down the output load to low logic state. SPICE N and PMOS transistors, as shown in the figure, are modeled with their material, physical and process parameters. As shown in the figure, by instantiating MOSFET SPICE models, a SPICE inverter model is generated. Using transient response simulation process, DC transfer characteristic is generated from which CMOS inverter static parameters are evolved. As shown in the figure, transient simulation of CMOS inverter generates the DC transfer characteristics. The DC transfer characteristic is plots between output voltage against the input. It is a key static characteristic that illustrates the inverter transitions between logic and defines important parameters like noise margins and threshold voltage. From the transfer characteristics, we observe that in the flat regions of DCT curve, the inverter output is stable at either logic high or low states. In transition region, both NMOS and PMOS are conducting and the output is in rapid transition state. The DC transfer characteristic helps designers to analyze robustness of logic levels and generate noise margins of the inverter. Dynamic characteristics of a CMOS inverter exhibits the switching behavior, that is, signal transitions between logic levels. These characteristics are vital for evaluating the dynamic performance of speed and power efficiency of the gate. Some of the key dynamic parameters are: input transition time, output transition times, propagation delay, max load capacitance, power dissipation, etc. These dynamic characteristics are typically measured using simulation models like SPICE or TLM and are crucial for timing analysis, optimization, and design validation of high-speed digital systems. A general timing model generation procedure for the setup shown in the figure is presented below. Design setup. Use a SPICE-level netlist or extracted view of the device under test CMOS gate. Include parasitic and transistor parameters from process design kit. Simulation environment. Applying input stimuli with varying slews input transition times. Sweep different output load capacitances. Measure propagation delays and output transition times. Data extraction. Record delay in transition for each input and output combination. Use this data to populate the timing tables. The timing model of a CMOS inverter predicts how long it takes for the output to respond to changes in the input. CMOS logic gate models can be classified as linear and nonlinear models. Linear timing model, LTM, assumes a linear relationship between delay and input transition time, output load capacitance. Mathematically, the linear model delay is expressed as sum of the delays of intrinsic delay, that is, the gate's internal delay without external load capacitance, input slew dependent delay, and external load capacitance dependent delay. The total delay of the CMOS gate can be expressed as sum of A times intrinsic delay plus B times input slew plus C times output load, where A, B, C are the constants obtained from SPICE simulations. The advantages are it is simple and computationally efficient. The limitations are: it is accurate for deep submicron nodes. Cannot model nonlinear behavior accurately. A table lookup model is built by simulating a logic cell, like a CMOS inverter, across a range of input transition times and output load capacitances to create a 2D matrix of delay and output slew values. The steps involved in creation of TLM are as discussed below. Define the sweep parameters. Select discrete values of input slew. Select discrete values of output load. Run SPICE simulations. Simulate the gate for every input slew and output load pair. Record delay high to low and low to high and output slew. Populate lookup tables. Fill 2D array matrix form. Store tabulated data in format like in .lib file. Characteristics of TLMR. Accuracy, high fidelity due to actual simulation data. Nonlinearity, captures both linear and nonlinear behavior. Interpolation, intermediate values computed using interpolation. Coverage, based on predefined PVT operating conditions. TLM and NLDM refer to the same kind of modeling. NLDM is essentially a nonlinear TM, more advanced and accurate than linear models. Power dissipation in a CMOS inverter arises mainly during switching activity to charge and discharge load capacitor. They can be broadly classified into three types as described below. Leakage power dissipation. A CMOS gate in non-operating or static condition carries sub-threshold and gate oxide leakage currents that lead to static power dissipation. Dynamic power dissipation. A CMOS gate during switching charges and discharges the load capacitance that leads to switching power dissipation. It depends on the operating supply voltage, switching frequency, load capacitance, and switching duty cycle. Short-circuit power dissipation. Due to differences in switching timings of P and NMOS transistors, during switching transition, an overlapping conduction of both the transistors leads to short circuit across supply, leading to short-circuit power dissipation. The total power dissipation of a logic cell is the sum of leakage, dynamic and short-circuit power dissipation. The figure shows the TLM model of CMOS gate power dissipation. From model we observe TLM displays leakage and short-circuit power only. Gate leakage power for gate is characterized and presented as a single value. Whereas, the short-circuit power as function of input slew and load capacitance is presented as lookup table. As the dynamic power is dependent on several variable parameters like load capacitance, operating frequency, duty cycle, etc., and hence cannot present it in model, but depending on the operating conditions, is computed by timing analysis tool. In CMOS gate, switching current is not constant, but varies in piecewise current segments and depends on operating conditions of input slews, load capacitances, output voltage, time, supply voltage, temperature, process corners. In composite current source models, transition current is broken into sampled waveforms and are modeled as a sum of controlled current sources. Hence this model is known as a composite current source model. The pre-characterized, condition-dependent, current waveforms offer high-fidelity representation of gate switching behavior. CCS model provides a composite waveform that more closely resembles the real switching behavior of a CMOS gate. CCS tables store current versus voltage, pre-characterized waveforms for rising and falling edges. During simulation, these waveforms are interpolated to match the actual transition scenario. The composite, pre-characterized, condition-dependent, current waveforms offer a high-fidelity representation of gate switching behavior. These models very effectively characterize nanotechnology devices. The effective current is not the exact physical current waveform from a full transistor-level simulation but a mathematically derived approximation that captures the essential characteristics of the gate's output drive strength over time. In ECSM, effective means a simplified current profile that approximates the actual output current behavior of a gate under various loading and input conditions, balancing accuracy and computational efficiency. Brief comparison of CCSM and ECSM is provided below. ECSM typically models only output current, while CCSM for higher accuracy models both input and output waveforms. In highly nonlinear or low-voltage processes, ECSM might not capture fine-grained waveform shapes, affecting timing closure. In high-speed and noise-sensitive paths, ECSM is less accurate than CCSM. CCSM uses full current voltage waveform tables for in and output. We will now have an overview of various libraries employed at various stages of design and verification process, and they are as discussed below. Logic, standard cell, libraries contain basic gates like inverter, NAND, etc. Includes timing, power, and functional models that are used in synthesis and simulation. Physical libraries provides layout views, placement grids, and cell footprints used in placement, routing, and DRC/LVS checks. I/O libraries include specialized pads, power, ground pads, ESD protection, and level shifters. Characterized for drive strength, slew, and ESD tolerance. Macro libraries includes memory macros, PLLs, clock dividers, etc. Typically provided as black box models with verified performance and behavior. The figures display examples of different types of logical and physical layout models used in VLSI design methodology. Figure 1 displays the SPICE model of a NAND 2 gate. Figure 2 displays TLM model of an inverter. Figure 3 displays the physical layout of a NAND 2 gate from a physical library. Timing libraries, TLMs, provide delay models like linear delay model, LDM, or nonlinear delay models, NLDM, for accurate timing analysis and are used in STA tools for timing closure. Power libraries contain dynamic, leakage, and short-circuit power data, and used for power estimation and power-aware synthesis. Multi-voltage and multi-threshold libraries support low-power design techniques using cells with different threshold voltages or operating voltages. Liberty noise models, standard.lib format libraries that include height/width sensitivity, crosstalk delay impact, delta delay, and slew models, output waveform sensitivity tables. Thanks for your time. Hope this video has been helpful in appreciating CMOS gates, characteristics, characterization, models, and types of libraries in VLSI design flow. Thanking you once again and hope to meet you in upcoming video. Bye for now.